All right, I think I'm going to start. Okay, so let me step back for a second and remind us where we're going, since we're certainly not going to get there. So just have an idea. So we've been discussing this, this four-dimensional arithmetic quantum field theory, whatever that means, of automorphic forms. So it's a theory that knows on the theory of automorphic forms. That's kind of what you get on arithmetic free manifolds, and it has all these other structures. We've been trying to spell out as much structure as we can out of this. What kind of things does this theory do on various manifolds of different dimensions? What kind of things, what kind of structures in the theory of automorphic forms does that relate to? And I'm going to do a little bit more of that in the next hour. But where we eventually want to talk about is the Langlands correspondence. And the Langlands correspondence is, very crudely phrased, schematically phrased, as something like an equivalence of four-dimensional arithmetic quantum field theories. So it's giving a different description of the same theory of automorphic forms in a dual way. And this is maybe again, this is what people usually call the spectral side or the Galois side. This is the automorphic side. This is built out of, let me say it very crudely, I'll say more later, built out of, if you'd like, the algebraic geometry of spaces of Langlands parameters, which are roughly something like representations of Galois groups, representations of Galois groups into this Langlands dual group. We started with the group G, and there's a Langlands dual group, which have appeared on the board without being defined a few times. So we can say more about that later. But just to say very, very crudely, the Langlands correspondence, or this is the kind of electromagnetic duality. This is the Langlands or electromagnetic S duality, is some phrase, is some kind of equivalence between these arithmetic quantum field theories in four dimensions. And so, in other words, it's giving a different version of the theory of automorphic forms in terms of Galois representations. And so the motivation, so I would like to spell out a little bit of this, but kind of what I wanted to talk about concretely, so what we started last time, and I'll talk about more, is one of the aspects of the theory of automorphic forms is the theory of periods. So one aspect of this theory, which we started discussing, was the theory of boundary theories, in the sense that Brian was explaining. Boundary theories in this thing, as I started saying, recall, have to do with the theory of periods of automorphic forms. And so if those correspond to boundary theories here, they should have a dual description. What are the boundary theories on this side? And the kind of punchline is that the boundary theories here have to do with the theory of L functions of Galois representations. And so what you might hope is that by thinking of the theory of periods in this kind of structured way as something being about boundary theories, that it will tell you something about how to match periods of L with L functions. If I have a period of an automorphic form, that should correspond with some L value of a Galois representation, and you might hope that this will help you predict which. So we want to get a bunch of formulas of the form, like period of an automorphic form should be equal to the L function. And when I say L function, I really mean L values. The S has consistently not been here. So the L value of a Galois representation, the Langlands correspondence kind of tells you how to relate these two, and that what I'd like to kind of extend that to telling us which periods should relate to which other functions. So this is what we kind of try to make prediction. This work I mentioned, make a lot of conjectures inspired by this formalism in this paper with Sickle Reeds and Beckett. So that's kind of the agenda. Yeah.
What does the S? Does the S have any meaning?
Yeah, so as Mignon explained, the S can be thought of as, there's families that you get by twisting by powers of cyclotomic characters. So that the integral shifts of S have to do with just changing of gradings. There's going to be some everything is going to have some grading and correspond to normalized by shifting the grading around.
So the S is the thing you're taking the value at?
Yeah, so here I'm really thinking of like an L function that you'd like at 0. So, suitably normalized. Maybe someone else would call it critical. Yeah, and if it's integral or half integral or something, let me
Can
know.
I take a non-integral shift?
I mean, you can certainly, you can think of the S dependence is given by twisting by powers of the cyclotomic character, so you can incorporate that. But our theory has nothing at all to say, I think, about S dependence at all. I mean, it's completely orthogonal, I think.
If in theory, you could try and investigate like families of cyclotomic characters or something, or.
Cyclotomic characters of power S. I mean, that's where the appears. You're twisting by that. So physics, I think the physics were to say that you can introduce a fugacity. That's a cool word that I don't really know what it means, but I think that's how the S appears.
So all the periods you have are related to Eulerian objects.
Yeah.
And sometimes there are interesting periods that are not. Are those at all incorporated into your theory?
I think things that are at least close. I mean, certainly, like, you know, what we get are things that we get things like sums of L values in here, I think. Okay, I don't really have a good answer to that, but I think there's. Let me just stop.
What's the meaning of the word Eulerian in this context?
Well, has an Euler product, so the L function is something that has a product, and I kind of was going to say the word Eulerian last time. I put in, you know, so for us these periods have to. I was starting to say last time, so maybe let's. Okay, that's actually a great transition. Where do these periods come from? The data I said is I want to fix an action of a group G. I have a G variety X, so G was my group. I have a G variety X. Really, again, this fits with what Brian is saying. I'm secretly not thinking about X. I'm secretly thinking about, let me call it M, which is the cotangent bubble of X. And this is how better to think about this as a function of M rather than X. And this is a Hamiltonian G space. It has a moment map to the dual of the Lie algebra that's equivariant for the group. This is the basic example of Hamiltonian G space, is the cotangent bundle of just ordinary G space. I'm going to suppress this for much of the time and just write it, suppose it's polarized, and write it as a cotangent. Given a G space X, we're going to construct something like a boundary theory. So this is the theory of X periods. And let me just to connect to your question, one of the things I was saying is that we need some strong finiteness conditions on X for this theory to be well behaved, particularly for it to have a chance to be Eulerian, for these periods to factorize as an Euler product. That's a very, very strong, and that's a kind of TFT type thing. It's a kind of locality. And that kind of locality basically requires X to be spherical. So the kind of X's that will appear, X will be spherical G variety, which means it has finitely many orbits for the Borel subgroup. It's one way to say it. There's several ways of saying it. I'm not going to get a lot. I'm not going to have time to get into the theory of spherical varieties very much, but just to say, there's a very strong finiteness conditions you require on the X for this to be a well-behaved theory. We work with these M's. We give an adjective which we call hyperspherical, inspired by the word hypertoric. Toric varieties are spherical varieties for a porous. So this is kind of a version. So really, you shouldn't be working with X. You should be working with M. But there's some very strong finiteness conditions. We impose more than is needed in our work. Ideally, there'd be much more general stuff, but we work with something we can work with. But anyway, but that's necessary for the Eulerian to be Eulerian.
You said the spherical property has to do with factorization of the period.
Yeah, it has to do with this kind of multiplicity. You need this kind of uniqueness. To write something to the fact that if you want a period to have something to do with an L value, you need some kind of this multiplicity one property.
Oh, the multiplicity one property.
Yeah, and that's where spherical comes in. Yeah. Okay. So all right. So what is this?
Are there places in the theory of two-dimensional field theories where we see spherical rather than hyperspherical playing an analogous role as a finiteness condition?
I don't know. The ways in which I know that spherical, I can tell you cool things about why spherical is needed, but they somehow need more structure. I don't know how to see it just in purely in mere symmetry. So I don't know that there's anything special there. Okay. So eventually what I want to do is make these kind of, I guess while I still have it here, the kind of predictions we want to say that the periods associated, I'm gonna think about this letter M. Really, maybe I could think, M is the cotangent of my X. I'm always gonna write things in terms of X, but let's just, I don't know, it's nice to have this notation. The idea is that the period for M, that's a boundary theory for this automorphic theory, in the sense that we're gonna spell out more. And that means that there's a dual boundary theory here, just whatever an equivalence of field theory is, a boundary theory is something that makes sense as part of the structure of a TQFT. So you'll get a boundary theory here, and the kind of conjectures that that boundary theory have a very similar form. It's given by, again, Hamiltonian action, but now it's a Hamiltonian action for the Langlands dual group. And that's kind of the rough kind of, we kind of make a meta conjecture that contains a lot of different statements, which is meta conjecture is that duality between the period associated to Hamiltonian G-space and theory of L functions associated with the Langlands dual Hamiltonian G group space. That's kind of that's a summary of our paper in one diagram. We finished. All right.
That's the whole lecture?
Yeah, exactly.
Make sure. So that statement is the statement that the equivalence takes the period.
Well, it's a lot more than that. That's the statement evaluated on a Riemann surface, but it's this is a whole four-dimensional theory. This boundary theory has a whole lot of different structures to it, and that's what I'm going to do in this lecture. There's a whole lot of structure here, and all of that structure. So this is a huge family of conjectures, right? This tells you can evaluate this on any arithmetic manifold with boundary. You get some and all these compatibilities between them. All the whole TFT structure here is supposed to match with this TFT structure here. So it's a lot of conjectures in different settings and a lot of compatibilities between them. Yeah.
So I should think of this boundary theory as some kind of codimension 3D factors.
Yeah.
So
Codimension one. I mean, it's a three-dimensional defect. Yes.
sorry, three-dimensional.
Yes.
defect. So not every three-dimensional defect arises in this.
No. So this is
it's kind of special. Like there's some like special property you're saying that like in this case, defects arising from such Hamiltonian G varieties happen to match up with defects arising from Hamiltonian G check varieties.
That's right. So yeah,
There's no reason for that to happen.
It's not totally random. I mean, so Gallardo and Whitney studied in the physics context. Gallardo and Whitney studied S duality for boundary conditions, and in general, you have all kinds of boundary conditions that don't come this way. And in general, the duality is complicated. What I will say, and this is something I hope to get to. There's a formula. There's an algorithm you can write. Given a boundary theory, I don't care where it comes from. I can write a space M check. So it's not completely random. You can always construct, as you know, you could construct an M check out of your boundary theory, and then you can hope that the duality takes your theory to the thing you build out of that M check. And we expect that's true we conjecture that's true for these hyperspherical varieties.
So sorry, what is PM and L?
So these are boundary theories. So I'm talking about boundary theories. This is the theory of periods of automorphic forms associated to M, which is a Hamiltonian G space. Hamiltonian G space. And in my examples today, that is always going to be the cotangent bubble of just G space, just to make life easier, make it twisted in the Whittaker case. But anyway, this is basically a G space, and my X is going to be very special. It's going to be spherical. So it's a very special class of boundary theories. And the L here, this is something I haven't discussed at all, and I might not even, hopefully we'll get a bit to it. This is the Langlands dual, S dual boundary theory. And the claim is this is the theory of L functions. So this is the slogan that periods of automorphic forms associated with M match with L functions of Galois representations associated with the dual. So you get a collection of formulas that tell a period. I mean, and by the way, everything we do is conjectures. There's a lot of conjectures, no theorems, but we predict, as various periods of automorphic forms should equal to certain L values. And it's sort of a kind of machine to tell you which should match what. Okay. So that's the executive summary of what's in our paper. Now, what I'd like to do now for the rest of this hour is say more about this theory of periods and spell some of the structures, and then explain how you can try to extract some of the dual data. Yeah.
I don't know what a spherical people is.
It's a non-abelian version of the toric variety. So the spherical means that the Borel has finitely many orbits. has finitely many orbits. It's a strong finiteness condition. And it includes lots of spaces, like basically includes a lot of the spaces you love in representations. It includes flag varieties, includes symmetric spaces, and it includes toric varieties in the Abelian case, but there's a lot of interesting examples. The group is a spherical variety for G cross G. And there's a lot of more exotic, interesting things. For example, in number theory, people love the Gann-Gross-Prasad example. There's a lot of examples that have to do with restriction problems in representations. Multiplicity one restriction problems in representations, they are captured by spherical varieties. So there's a lot of interesting examples, which I won't have time to describe. Okay, so let me just say a little bit about what periods look like. So I fixed a G variety X, and what are the kind of thing you could do? Well, last time I drew these kind of pictures where I think of a period as being some kind of integration contour for automorphic forms. There's some kind of space you can integrate automorphic forms on. Let me say it in a more geometric way, and I'm going to say basically I want to say what the period does. In the unramified situation. So the unramified situation,
David, in this example, that picture, you really should only be integrating weight 2 modular forms, right?
No.
But you want one forms on the modular curve.
You have to be careful how to normalize the measure, right? I haven't explained to you what I mean by integration, where I get the measure, but this is something I can do in all holomorphic. They don't need to be holomorphic modular forms that I can. This is something I generally do.
Okay.
Let me not. But this is something general I can do for all holomorphic forms. Okay. So here's the kind of geometric description of what a period does. This is a kind of a classical arithmetic picture, but in the function field setting, there's something very nice you can do. Remember, the function field setting, automorphic forms have to do with cohomology classes of some space of G bundles on a curve. So that's the analog of the this locally symmetric space for a global field. And what you could do is I can construct this following space. This is the space of G bundles on the curve plus a section of the associated X bundle. So you have a G bundle on the curve. You can talk about the Gx on X. You can talk about the associated X bundle. You can look at a section. Or people who like stacks, this is just a maps from the curve into the stacked X mod G. That's just a more succinct way of saying that. And there's such a map associated to X. And what you can do is you can take a cohomology class here, you can pull it back and push forward to a point. Integrate. That's what the X period is. You take classes here. That's a version of integrating on an automorphic form on this sublocal symmetric space. Take something, pull it back, and push forward to a point.
You keep pulling out the cohomology.
So cohomology classes, that's what my automorphic forms are here. There are cohomology classes here. And I'm not going to talk about how to normalize measures and stuff like that. So but I pull that back and then integrate to a point. So that's a functional on the cohomology. So I have a map from the automorphic forms associated to sigma to grand field, which is let's call this the X period, and that's given this by this pulling.
So you have to. What do you integrate them
over this space? You push forward to a point.
Oh, so it has to be the degree.
That's what I'm going. Yeah. Okay. So that's what the X period is, and that's just to emphasize. I want to write this formula to say I didn't need X to be a homogeneous space. Right. So where X is a homogeneous space, you can think of there as just being a sub-locally symmetric space. But you don't need it to be a subset. So here, that's the kind of schematic. Let me give you one example.
Sorry, David, before you do that, I think this question came up several times.
Yeah.
How do classical automorphic forms fit into this equation?
So a classical automorphic form, I'm thinking of say a homological automorphic form. So
let's just take a function.
Oh, sure, yeah. So I take a function on this and I pull it back to here and I integrate.
You just integrate.
Yeah.
Okay.
Yeah. That's it. That's what a period is. So again, here, in the case of a locally symmetric space, this guy, that's the locally symmetric space for the torus sitting inside of the locally symmetric space for the group. I take a modular form, restrict it to this vertical axis, and then integrate. So that's the version of that. That's what this map is.
But you do need a measure.
Yeah, but I'm not going to talk about it.
Okay.
Yeah.
I mean, I'm pretty sure that, weight two forms correspond to
Let me not address that.
one form.
Yeah, but this works for arbitrary cohomology classes, and so other weight forms can also be interpreted in cohomology classes with coefficients into local systems in this space, and you can do this, evaluate the period on both. Okay, so let me just give an example, which is the kind of the Theat, called the Theat period, and maybe you could call it, Riemann, Theat, Kurosawa, depending on what you're calculating exactly. But an example of this period is I take the group G to be GL1, a multiplicative group, and X to be the affine line. So the Hamiltonian G space is a T star of A1. And in this case, this map becomes something very simple. So bun G just means line bundles. So look at the space of line bundles. And what is this bun GX? It's line bundles with a section of the associated A1 bundle, aka sections. So maybe doing some stagnance or something. This was the union of the symmetric powers of the curve. That's what this map is. And so you take your automorphic form and you pull it back to here and you can do it. So that's an example. So or if you like, you can by adjunction, whatever, you can think of taking the push forward of the constant function 1 and integrating a form against that push forward. And this is exactly the kind of thing that appears in Riemann's. So the Theat's thesis and Theat-Iwasawa statement is that kind of all abelian L functions. So you can like Riemann zeta function, Dedekind zeta functions, Dirichlet L functions, and the most general word is Hecke L functions are given this way. Here, so here you're looking at this was the version of this Edel class group. You have something on the Edel class group and you integrate it against the theta series. That's this push forward. Oh. So the integral of a Hecke character against a theta series, I'll return to this formula in a little bit. That's the zeta function, L function, associated to this Hecke character. So that's what this formula is doing.
What is chi? Chi is it?
Chi is a Hecke character. It's a character of the Edel class group.
There's a test function in this story.
The test function will appear in a second. Yeah, that doesn't appear in the unramified situation.
You're integrating over the Edels or something?
I'm integrating over the Edel class group, which is pick. The test function will appear at a ramified point.
Yeah, right.
Yeah, right. Okay, so this is
before you arrange that. Sigma here is a curve over finite field or over algebraic function.
Here's sigma. So my notation is sigma is a curve over a finite field. Sigma bar is a curve over the algebraic closure. So here I'm doing the theory. Yeah. So here, this formula, I was trying to tell you what the period is on a 3 manifold. So on a 3 manifold, I have a vector space, and the X period, if you like, is a functional to K. That comes from this picture of a boundary. Here's my 3 manifold, across an interval. I put the boundary condition. This is if you like, this is my boundary theory. And I'm telling you what this is on a global arithmetic 3 manifold. For example, a curve over a finite field. That's the setting. So that's, yeah. Now, again, being a boundary theory, part of what it tells me is that I can do this not just on a particular number field, but it's something that makes sense on the data of X, or this data piece of X, is something I can evaluate. This is, if you like, what piece of X of N is. I can evaluate this on any arithmetic 3 manifold. I get a functional on the space of automorphic. So it's a consistent collection of functions. It's not just a single functional on a particular number field sake. That's part of what makes this a boundary theory. But now you can ask, okay, so maybe now I'll get to your so now we're supposed to replace this 3 manifold by a 2 manifold. And so now I should, this boundary theory should have, I basically draw the same picture, a 2 manifold across an interval, and I put this there. So there should be a version of this period functional in any setting, right? This period should extend to something in the entire field theory. So I told you what kind of thing it does for 3 manifolds. what kind of thing does it do for two manifolds? So let me, there's kind of two different kinds of two manifolds. I mean, there's several, but maybe let's, so let me talk about the local Langlands version. So I'm going to take a local field. So I take, FV is a local field. That's my two manifold that I'm thinking about. Maybe think of, think of PP or something finite over PP. And now this is really what I'm kind of rewriting what I think an observation of Socrates and Venkata, one of the in their book, they have something that they think of as they emphasize as the local version of periods, of the theory of periods. And that's kind of the beginning of what they're doing is there's a natural local thing of space of periods, which has what kind of thing should this be? Well, this AG, this automorphic form theory is roughly something like representations of this chaotic group. There's more stuff, maybe let's not worry about it, right? But this category is basically the category representations of the chaotic group. And so what should you be doing? The period should be a functional on this, right? This is my AG is this category. So I want a functional. So I need a functional from this instead of the K. I should now be a functional to K vector spaces, right? And one level up, that's what this period should do over two manifold. It should be a functor, exactly. But I'm thinking about, I'm trying to think of that as a functional, a linear functional on this category. It's a way of attaching a vector space to a representation. Well, as you say, these functors can be represented. These functors are representable. What is this functor? And this again is what Socrates emphasized. Well, given this space X, I can construct a representation. Namely, I look at smooth functions on X. Smooth and make chaotic sense, locally constant functions. So I look at smooth functions on X, and that's a representation of my group. That's a smooth, it's very, very far from an irreducible representation. It's a big representation. But I can think of the functor represented by that. I can take of representations from any representation. So I can think of B going to, in other words, I'm just looking at multiplicity. I'm asking about multiplicities spaces for representation in this big thing. In other words, I'm doing local harmonic analysis. I'm taking this representation and trying to decompose it. So the local harmonic analysis of, say, symmetric spaces, for example, right? That's a good example. Can be thought of as a local version of this theory of periods. That's what this functional does. That's what this function is on the local field. And again, Socrates Venkata emphasized how that interacts nicely with the global theory of periods.
So I'm lost. Is X defined over FV?
Yeah, my X was going to, I've been totally, my X's are really going to be defined over the integers or something. So I'm going to be able to evaluate it.
But this, I'm trying to make.
But yeah, X is going to be.
X is going to be defined over FV. So
X is going to be.
G of FV acts on it.
Yeah.
Okay.
No, yeah, sorry, I should say X is defined over whatever. I can look at its FV points and I can look at smooth functions on this. And that's a good example of a representation. That's classic example of representation of chaotic groups come this way, and you could or real groups, right? You could take your favorite symmetric space, look at the real points, and look at the harmonic analysis question of which representations appear in functions on that space, and that's what this functional is doing.
So this form is now finite.
Yeah, so that's now I'm going to want to have strong finiteness conditions on X, right? If X is arbitrary, this could be crazy. X being spherical is basically going to tell me this is, I think, equivalent to all representations of finite, all irreducibles having finite multiplicity. Yeah. So yeah, it's going to be finite because my X is super special. That's one reason why spherical is important. Okay. So that's now if I'm doing another kind of two manifold is a Riemann surface, or a curve over algebraically closed field. And then my AG is now some category of sheaves on the space of G bundles on this Riemann surface. Now we're in the setting of geometric Langlands. And then again, I want some kind of functor to vector spaces, the same kind of vector. That's what my period should be. Well, and again, it's easier to not dualize, to just think of representing it by an object. I'm really going to give it, this functor is going to be from some particular sheaf in here. So the period is, I'm dualizing, right? I'm thinking the functor this functor, I'm representing it as into some sheaf. So there's a particular sheaf here, and the sheaf is given by the exact same formula. I want to give a sheaf on bun G. Well, I have the space bun Gx that I've defined before. Right, G bundle with the section of the X bundle. I could take the push forward. I don't know, maybe I should be a little, probably, I think I want to shrink push forward. Yeah, okay. I can take the shrink forward of the shrink push forward of the constant sheaf, and that's a sheaf. That's my period sheaf. Or if you don't like that, you can take any sheaf here, pull it back, and push forward to a point. That's the formula I gave before. Take something here, pull it back, push forward to a point. That's represented by this guy. So that's the geometric Langlands version of a period. So, okay, now, but again, I was trying to explain there's lots and lots of structure to this field theory, this arithmetic field theory. So boundary condition will give things that live in every context, but also have really interesting relations between how that all these compatibilities of the field theory structure. I don't know how much time to spend on this. I guess what I wanted to get at is some of the more. There's some really interesting things when I just wanted to emphasize that some of the things you really care about in harmonic analysis on spherical varieties appear naturally out of the field theory. Two things, so maybe I'll just say two things that I want to get at is the Plal measure, so there's kind of the Plal formula for the spherical varieties. That is something of course you can ask the Plal question here. What I want to claim is it's really something that naturally fits into pictures I could draw in the field theory. It's something I could get at using the field theory. Therefore, it's something I'm going to know what to do under duality with. And the other thing is theta series, construction of theta series. And I claim that these are both things that make a lot of sense in the field theory. So maybe let me just draw some pictures. I don't have time to get in this full detail. Again, this is all in our paper, but actually, this is all explained in Appendix D. So I'm localizing the search. So
when you say that you're claiming that the Plal measure.
Yeah. So what I mean by what do I mean by Plal formula here? So there's many things you can ask. What I mean is, so for example, this is something that was described for spherical varieties in the paper of Sekularides. And what is the question? Let me just ask, what is the Plal formula? The question I mean. So I take ads of FB. Let me write. I'm going to just write QP, just to make it look. QP is just my notation for a local field, but it looks better this way. So you take X of QP. One thing you could do is you can look inside of here. Is you can look at there's inside of smooth functions on this space. One thing you could do, for example, is you could look at the spherical vectors. So you can look at and by the way, this is the third appearance of the word spherical in these talks. Third unrelated things. There's spheres in the TFT, there's spherical varieties and spherical vectors, and they're all three independent uses of the word sphere. But you can look at the spherical vectors. When you study harmonic analysis, you can look at the maximal compact subgroup. You look at fixed vectors for the maximal compact subgroup. So this is somehow a much simpler object. This is the kind of unramified part. This is now a module just for the spherical algebra instead of the whole group. We cut down from the big representation group to a module for the spherical algebra. That's something more concrete. And inside of here, there's a basic function. What's it called? Let's look at delta sub x. There's a basic vector here, which is just the constant function on x z. There's kind of a basic vector in this representation. And what you mean by the Plal decomposition, this is just like in the Plal measure for a group. You want to ask the Plal decomposition of a.
So what is the characteristic function?
Yeah, the characteristic function of CP, and you want to understand how this decomposes. And so the kind of things you might calculate is you take your favorite elements in the Hecke algebra and act on this guy and ask to calculate all their inner products. That's the collection of all these inner products under the Hecke algebra of this function. This is what encodes the Plal decomposition.
Is it V and W? Okay.
Yeah, so these are my labels for elements PV and PW. I'm calling them that because P and W are simply representations of the Langlands tool group. But that's just a label for these Hecke operators. So that's what I mean by Plal measure. so this collection of all these data, that's this Plal decomposition of the basic vector.
But you want to write this as an integral with respect to the Plal measure.
Well, you like, this is actually like the Plal formula, I mean, basically this is the question. This is what you'd like to describe in terms of the spectrum of the Hecke algebra. That description is the Langlands course duality here, but here I'm just asking this, I want to think that these objects, these kind of things,
That itself is natural.
is completely natural from the TFT. So let me just draw some pictures, and not elaborate on them very much, but I just want to, just draw some pictures of things you can draw. So just to have some schematics, right? So the circle, we said we look at all this is categories, or with this action, this local feature. That's my two category attached to a circle. Inside of here, I have a basic object, which is the disk, which is a particular thing, which is streams of the affine Grassmann. That's an unramified representation. And this is acted on by the line operators, which is the value on the two sphere. The value on the two sphere is the Hecke category. Okay, so these are pictures we discussed last time. Then I said, well, we could take a trace of Frobenius. We can cross with this, basically cross these pictures with a circle. I'll just draw the same pictures across the circle, right? And then you have this solid torus. And then you could take, I don't know, a two sphere cross S1. So the same way, there's going to be now it's a category with an object, and that's something that acts on it. This is now the representations, the category representation of my group over this local field. Roughly, this is the space of functions on the affine Grassmannian. That's the unramified representation. And then this is the Hecke algebra. Okay. So far there's no boundary condition. So these are just some of the pictures we discussed last time, things you can draw in the TFT. And now I want to put in a version with boundary, and I'm not going to explain exactly the calculus of my pictures, how this part of the picture of cobordism hypothesis or topological field theory with defect. So I'm just going to draw versions of these pictures where I'm going to think of my boundary condition as, let's say, purple. So what are some objects I could take purple boundary to a disk? So this is playing the role of a two manifold that gets attached to category, which is the category of sheaves on this X, the p-adic X, that are G of O equivariant. So that's a module category. So that's acted on by this by the second category. Yeah.
Fixed by G or O?
Yeah, equivariant, or if you'd like, maybe just think of sheaves on X of FV in the coset space. So that's a natural category I can look at. Inside of there's a basic object. There's a basic object which can be drawn as, I don't know, there's a picture like this. So this is going to be, there's an object in here which we call it, which is kind of the basic object, which is the constant sheaf now on X of OV. And then one more picture I could draw is, okay, I'm not sure if these pictures are helpful for anything. What am I trying to convey with these pictures? I'm just trying to convey there's a lot of pictures you can draw, and they convey basic structures that you care about in the harmonic analysis. This picture, maybe let me explain. Okay, so there's a picture here, and this object is some version of endomorphisms of this basic object as an algebra object in the Hecke category. These are pictures you can extract out of these things. And this is probably very unfamiliar, so let me draw the function theoretic level, right? Again, I'm going to take trace of Frobenius. Now it'll be very classical objects in harmonic analysis. But when I cross this, what do I get when I cross this picture with this circle? I get like a solid a purple torus, which is filled in. That's the space of functions on X of FV mod G of OV. That's spherical functions on my spherical variety. So that's how it appears in the TFT. And inside of there, the same picture across the circle, let me not draw it. There's a basic vector that I drew before, the characteristic function of X of OV. Okay, and finally, this was all to draw the following picture, which I really can't draw terribly well. I want to take S2 cross S1. Okay. So this is my picture for S2 cross S1. I'm taking that across the circle, right? And then, and I claim that what this picture tells you, this is where the Plal formula lives. This picture is where inner products of delta X with Heck operators put in lives.
Wait, so that means the Wilson lines in there?
Yeah, exactly. So I put in some, thank you. Yeah, so really I put in some Wilson line here. And that's my Heck operator. Maybe I have two Wilson lines.
Wilson lines B and W?
Yeah,
Right,
these are my two colors, B and W, or two Wilson
The
lines.
top lines B and W.
And top line, sorry, I'm not, well, yeah, I'm on the A side.
And you're saying, I see. So you're saying that these boundary theories in tech,
Yeah.
the partition function on this four manifold
Exactly.
is, let's see, after all of
It's
this
inner-
bracket thing.
It's inner product.
Is that a complex number?
Yeah, exactly.
Okay, good.
Exactly. We're now in this picture is a four manifold, so I'm getting a number.
Okay,
And the numbers that you get in the Plal formula, they're part of the TFT. That's all this was supposed to convey. Okay. Now let me convey one more picture. There's only one thing more I wanted to do before doing Langlands. Let me go one more picture because I think it's really cool. And which is the theta series.
wait.
Yeah.
Before you go.
Yeah.
So I'm a physicist.
Yes.
Is there a formula? Is there an example of a concrete formula for this complex number?
Yes.
That's a mathematician's answer.
So there's a beautiful paper by Sicklerides called Spherical Functions on Spherical Varieties, which is exactly about calculating these numbers.
What is the simplest non-trivial example?
A point. Oh, non-trivial,
Point?
sorry.
I'll take it as long as it's non-trivial. Don't tell me it's equal to.
No, I
one
mean,
and everything
I don't
is a
know.
point. But
Okay, what's the simplest non-trivial example? I don't know. So I mean. Okay, let me address that.
okay.
There's many interesting examples. I don't know where to. It's a lot of SL2 examples that you can write down, but let me write down something about theta series. Because that's something cool that we didn't really discuss much. Again, this one only appears in Unit XD very briefly, but so what is that theta series? They're kind of canonical intertwining operators from these local representations appear in the spaces of automorphic forms. That's kind of the slogan, right? There's interesting local representations of the kind like functions on the spherical variety. There's canonical intertwiners from them into spaces of automorphic forms. I think of this as some kind of analog of something very simple but extremely important in representation theory. If I take any representation of a group G, there's a canonical map, the matrix element map, from V tensor B dual to the functions on the group. This is kind of one of these topological things that everyone in representation theory. That's some kind of canonical intertwiner of G times G representations. Right? The theta series is some kind of, this one can also be drawn by TFT pictures in 2D TFT. It's some kind of version. You can interpret it as this kind of picture. But in any case, there's a TFT interpretation for the theta series. So what is
coefficient?
I'm sorry?
The matrix coefficient?
Matrix, just matrix coefficients, yeah. So so the matrix coefficient map is this kind of canonical intertwiner. The theta series is similar, morally similar in TFT language, also similar. I take I'm going to try to write, I take my representation. So remember that what I attach sorry, yeah. So I have these. Sorry, that's not what I want to write. So there's canonical intertwiner between these functions on my spherical variety X of FV to a space of automorphic forms. So this lives in some space of automorphic forms, so ramified at V with full level structure at V. So what is the picture here? I'm thinking of taking my three manifold. So right, my space of automorphic forms is what I attach to an arithmetic three manifold. V is a prime. That's my picture of a knot. And so I'm looking at so if I look at the theory on the three manifold minus this knot, right? That's an object of AG on the boundary of the knot on this T2, which is basically representations of my group. Right. So if I look at space of automorphic, so this I'm just saying annoyingly, look at space of automorphic forms with full level structure at some on V, that's a representation of the group. Okay. Now, so this is acted on, so this space is acted on by the group, and the claim is that there's a canonical interpointer you can write like this. Okay. Now, the way people who write it in number theory, somehow they're not content usually to fix a prime. You could do this for finitely many primes at a time. I can do tensor product, over some set of primes of these guys. So you can look at the intertwiner for many of these at a time. Okay. Or really what you might do is they do over all primes, they look at Gellert points of X and look at functions. Again, don't take it too seriously what class of functions I'm talking about. A suitable space of function on here. Now we'll go to automorphic forms with a Gellert space of automorphic forms. A representation, this will now be an intertwiner for representation of that Del group. And what I wanted to claim is that these things are completely also natural from the TFT point of view. These theta series maps also have natural TFT pictures. Maybe I should write down just classically what is this map? It's some kind of canonical intertwiner. You look at X of the Adels or X of FB. Let me just do it with all the primes at once, just to be more concise. And here the space of automorphic forms is G of the Adels not G of the global field. That's the fully ramified space of automorphic forms. And there's a natural correspondence, which is something like this, G of the Adel times X of F. There's some natural correspondence you can write down this way. And the claim is that this also has a natural interpretation in terms of moduli spaces of bundles. This is a modular space of bundles with level structure at all, basically near every point. This is kind of maps from the puncture neighborhood of every point into X. And this is maps with a section. So this is an object that's like my bund GX. This is G bundles with a section of the associated X bundle just near away from my chosen primes.
I don't understand. You chose an F. What is this? You're working adelically. So
yeah.
What is F?
The global field. F is my global field.
Oh, I see.
So there's and you can write down a picture. So let me not. I don't really want to explain this very carefully with the time. And so basically, what I want to claim is that we had two things we drew. One thing we drew was the global period. The global period in my picture was what you attach to that's a bad picture of a three manifold, but this is my picture for a three manifold. That was the global period.
Wait, were you identifying the top and the bottom or not?
No, I'm writing a cylinder. So this is my three manifold across an interval, and I put my boundary condition on the one end. This was the global period. The local period was something like this. That was the representation. Functions on the p-adic representation was the local version. But now I'm going to look at the boundary condition where to draw this theta series, you need to look at a manifold with corners. And you need to look at something like this, and I'll get the picture wrong. But you draw some manifold with corners where you take a purple manifold. This is very schematic.
What are you doing? You're cutting cylinders out of this surface.
Yeah, so I have a Riemann surface where I've cut out some points, some cylinders. At those points, I'm putting in my interesting boundary condition. There's canonical manifold with corners pictures I can draw. I don't want to spell this out carefully. It's done in our paper, but just to claim that you can in this theory, you can naturally write down, and and this goes back to Mignon's, now just to finish up, why am I saying the theta series? Because, as Mignon said, that if you want to write the Riemann zeta function, you say it's, integral, well, or generally one of these zeta function, maybe chi could be trivial, but you integrate around something. That theta series is theta of some, I don't know how to write formulas. So it's theta of some Gaussian. Now, what is that's Riemann's formula for the zeta function. If chi is trivial, or the L function of the modular form is given in this way. What is this thing doing? This is exactly one of these theta series. It's going from L. I don't know my functional analysis either. Let me write. So I have a test function, a Schwartz function on the affine line over the real numbers, going to function on the L class group. And that's what the theta, and that's a classical theta function. That's the classical theta series. And in here, I'm taking the Gaussian. So that's the 1-point version of this construction. I'm just doing this at the real place. But you could have also done that Schwartz space, that adelic Schwartz space, and that's so this is where kind of classical periods involving matrix coefficient involving theta series. That's how they're incorporated into this TFT structure.
You understand, you're saying this map here, the theta series map, is explained in terms of that picture.
Yeah. So I'm just saying that there's I have this period which is boundary condition in my theory, and I claim that if I evaluate it on a two-manifold, I get an object in this category attached to a two-manifold, which in my case is something like representations of a Theatic group. So that's the local object. And then I'm claiming that, so then I have, maybe one way to say it precisely is this. Here's I can look at my three-manifold. So I look at the vector space attached to my three-manifold where I put X level structure plus X level structure at some places.
You just drew a picture just to the right of that formula.
Yeah, I'm trying to explain what that picture means.
Yeah. So
I'm saying you can look at the representation. I can look at automorphic forms where at every place I can impose on the automorphic form level structure. The level structure is given by an object of the local category. So the TFT picture, I'm just saying you could get a vector space, right? I want a vector space with a three-manifold. What is my three-manifold? I take this arithmetic three-manifold, I remove some primes, and add those primes, I insert my local data. So there's a vector space here, automorphic forms with X level structure, and the claim is that there's a canonical element in this. I don't know what to denote it. There's a canonical element in this space of automorphic forms, which by some duality, you can interpret as an intertwining map from the tensor product of local representations to the global fully ramified representation.
That's a period.
And that's, well, the period sheaf is the unramified version. What we talked about in the paper is there's no ramification anywhere, which is not so interesting in number theory. This is much more interesting. Now, this is what happens when you have some ramification. You have this theta series now. So this is the interpretation of theta series. So, okay, so yeah, so we have cookies and cheese and stuff and take our breath. And so what I want to do in the last hour, by the way, I've slipped into, kind of leaned into this accident of scheduling myself an extra hour. So, so afterwards, I'm going to explain a little bit about how you Langlands dualize all of this. Yes.